Okay, so at this point, we're going to talk about essentially the formation of aqueous solutions. And as we mentioned a little bit in our discussions of chemical reactions, essentially when you have an aqueous solution, you have water as the solvent. So water is one of the most common solvents found in nature. Uh, in many instances, water is sort of considered the universal solvent because there are many things that do dissolve in water. I don't know if I necessarily agree with that sort of distinguishing aspect for water, because I know of many compounds that don't dissolve in water, especially large organic compounds, and a lot of bioorganic compounds don't really show a lot of solubility in water as well. But a lot of the salts that you come across show either excellent solubility or at least some solubility in water. So essentially, water is quote unquote the universal solvent. And when you take a solute and you dissolve it in water to form a solution, you have essentially what is known as an aqueous solution. Now, let's go over some of the important aspects of water that apply to not only aqueous solutions, but as we'll see, solutions in general. So when we had our discussion of polar covalent bonds, one of the bonds that we talked about specifically was the OH bond. And we know that for the OH bond, neither the hydrogen or the oxygen are neutral. The electronegativity difference is large enough so that the electrons are shifted towards the oxygen and away from the hydrogen. So we know from our discussions there that the oxygen has a partial negative charge associated with it, and the hydrogen has a partial positive charge associated with it. Now, if you think about the structure of water, where we have hydrogen bonded to oxygen, bonded to hydrogen, both hydrogens in water have partial positive charges associated with them, and the oxygen in water has a partial negative charge associated with it. Now, when we had our discussion of shape, we talked about the fact that if an atom has two bonds and two lone pairs of electrons, which water absolutely has, the shape around that atom is bent. Okay, so water has a bent shape. So we look at the idea of the combination of water having polar covalent bonds and having a bent shape. That combination led us in our discussions previously to classifying water as a polar compound. So water is absolutely a polar compound because of the polar OH bonds that are present and its bent shape. Okay. Why is this so important in terms of the idea of classifying water as a polar covalent compound? Well, it turns out that solutions will form when the solute and solvent have similar polarities, have similar charge associated with them. Now, based on that, the general rule for solution formation is like dissolves like. In other words, for all intents and purposes, the solute and the solvent have to be similar to each other in terms of charge. Now, in essence, like dissolves like could mean some other things, like type of compound, for instance, like in the solubility lab, organic versus inorganic. But in reality, when you think of like dissolves like, most often what it refers to is it refers to charge, that the solute and the solvent have to be similar in charge in order for the solute to dissolve in the solvent. And we'll go into more about that as we go forward. So if you take a look at the table below, they talk about the fact that solutions will form when the solute is polar and the solvent is polar, and when the solute is nonpolar and the solvent is nonpolar, because in those two cases, the solute and the solvent would be similar to each other in terms of charge. On the other hand, solutions will not form when the solute is polar and the solvent is nonpolar, or when the solute is nonpolar and the solvent is polar, because in these instances, the solute and the solvent are not similar in terms of charge. Okay. So why do some substances dissolve in water? Some types of compounds dissolve in water while others don't. So in essence, we know basically that there are three different types of compounds: ionic, polar covalent, and nonpolar covalent. Let's talk about the ideas behind their solubility in water. First off, let's start with ionic compounds, which in this case would essentially be referred to as ionic solutes. Now, essentially, all ionic compounds show some solubility in water. There really is no ionic compound that is totally insoluble in water. Now, some of them will dissolve very, very little in water, while others will dissolve very readily, and a lot of it will dissolve in a given amount of water. So the amount that can dissolve in water will vary, but basically there's really no ionic compound that doesn't dissolve in water. So what is the reason that ionic compounds dissolve in water? Well, if you look at the example of sodium chloride, okay? Sodium chloride. So if you take a look at the structure here, they show you essentially the crystal lattice that would exist for sodium chloride as a solid. Most ionic compounds come in a solid form. And when you have these solids, you sort of have these crystal lattice type structures. In other words, the ions are really held together very tightly by the opposite charge between them. What essentially happens is that the water molecules essentially start to penetrate the lattice. And what they do is that they surround each ion and pull it into solution. Now, what types of attractions do you have here? Well, in general, your cations, which of course are your positive ions, they're going to be attracted to oxygen of water. And the reason why that is because the oxygen in water has a partial negative charge associated with it, and cations have a positive charge associated with them. So you could see, if this was an example of sodium chloride, you could see how the sodium ions would be surrounded by the oxygens of water, okay? On the other hand, your anions, which are your ions with a negative charge, they're going to be attracted. And let's see if we can write that A and C a little bit better. They're going to be attracted to the hydrogens of water. Because the hydrogens in water have what type of charge associated with them? The hydrogens in water have a partial positive charge associated with them. So here you can see that the chloride ions would be surrounded by the hydrogens of water. This process, where water molecules pull ions in, surround each ion and pull it into solution, this process is what is known as hydration. And essentially, your hydration is really the reason why your positive and your negative ions are able to dissolve in, or that why your ionic compounds are able to dissolve in water, because water surrounds the positive and negative ions that are found in the crystal lattice of this ionic solid, and by surrounding them, they pull them into solution. You can see that based on the following equation here, that if you take sodium chloride solid and place it in water, the ions separate into Na plus and Cl minus. Okay. Let's see what's going on. A little bit of a technical issue. So let's see if we can go back. Let's keep the notes. Let's play from the current slide. Okay. All right. So now let's take a look at your polar solutes and why some polar covalent compounds are able to dissolve in water. So a polar covalent compound such as methanol which has the structure of CH3 connected to OH. If we were to draw that out, you'd have carbon with 3 hydrogens attached, and then that carbon would be attached to an oxygen that has a hydrogen attached to it. That compound would be what is known as methanol. Now, methanol is soluble in water because it has a polar OH group to form what are known as hydrogen bonds with water. And essentially, hydrogen bonding with water is one of the key reasons why polar covalent compounds can dissolve in water. I'm not saying that they're going to, because there are other mitigating factors like size, and you'll learn that more if you go on and take organic and biochemistry. But essentially, one of the main reasons why polar covalent compounds can dissolve in water is because of hydrogen bonds with water. Now, in terms of a definition, what do we talk about when we talk about hydrogen bonding? Hydrogen bonding is the force of attraction between a polarized hydrogen atom in one molecule and a polarized oxygen, nitrogen, or fluorine atom in another molecule. And really, it's an attraction between hydrogen and oxygen and nitrogen. Fluorine really doesn't usually come into play with this. Remember, a sample of a polar covalent compound is going to be made up of millions of molecules of that compound. Okay, so if you think about water itself, you know, one of the things with water is you're probably familiar with is the idea of boiling water. When you go to boil water, especially if you're going to make a couple pounds of pasta, you know, you put the water in the pot, you put the pot on the stove, you turn the flame on, usually when you have the gas stoves. And, you know, the question is, does the water boil instantaneously? And the answer is no. Essentially, what are you waiting to have happen? You're waiting to essentially supply enough energy to break the hydrogen bonds that would exist between the water molecules. What would that look like? Well, essentially, it would look something like the following. Okay. So we know that the hydrogens in water have partial positive charges associated with them. Okay, and actually, let me redraw this a little bit, because we got to space this out a little bit more. Okay, yeah, maybe we'll draw that hydrogen like that and get rid of this one here. Okay, so hydrogens in water have partial positive charge. The oxygens in water have partial negative charges. So I'm not going to draw all those partial positive charges in. But essentially, based on the idea of opposite charges attracting, the hydrogen of one water molecule is going to be attracted to the oxygen of another water molecule, partial negative to partial positive. And essentially, you'd have that here, and you'd have that here. What force of attraction do you have between these molecules? You essentially would have hydrogen bonding. Okay, and the reason you would have hydrogen bonding is because you have a polarized hydrogen in one molecule attracted to a polarized oxygen in another molecule. And you have that here as well. That force of attraction is what is known as hydrogen bonding. So let's look at methanol in water. So here's the methanol in the middle. The oxygen of methanol would have a partial, let's see what's going on. The oxygen in methanol would have a partial negative charge associated with it. The hydrogen attached to the oxygen in methanol would have a partial positive charge associated with it. Now, one thing to notice is that there are hydrogens on carbon that are present in methanol. And as you look on the bottom here, one of the other questions that we pose is that why do the hydrogens on carbon and methanol have no charge and are not involved in hydrogen bonding? Because if you notice, there's no water molecules that are surrounding them. So remember, a carbon to hydrogen bond is nonpolar. The electronegativity difference is small enough that essentially the bond between carbon and hydrogen, the electrons are shared equally. And we know that in a nonpolar covalent bond, the atoms are technically what? The atoms are technically neutral. So one of the things to remember going forward is that hydrogens on carbon are never involved in hydrogen bonding because they are neutral. However, the hydrogen on the oxygen of methanol has a partial positive charge, and that would be attracted to an oxygen of a water molecule. Whereas the oxygen in methanol would be attracted to a hydrogen of another water molecule, which would have a partial positive charge. And again, both of these forces of attraction, as you can see in this slide here, are your hydrogen bonding. So since methanol is able to hydrogen bond with water, that force of attraction leads to methanol being able to dissolve, be soluble in water. So here's another diagram illustrating this. Essentially, you have methanol molecules that are attracted to each other by hydrogen bonds. You have the water solvent where the water molecules are attracted to each other by hydrogen bonds. And when you mix them together, now essentially you have some hydrogen bonding between methanol and water molecules. And that hydrogen bonding is going to lead to methanol to be able to dissolve in water. So hydrogen bonding is not the only reason why polar covalent compounds can dissolve in water, but really is the main reason why polar covalent compounds can dissolve in water. And then finally, aqueous solutions with nonpolar solutes. So now we're talking about nonpolar covalent compounds. So a nonpolar covalent compound, such as methane, CH4, is insoluble in water because similar forces of attraction do not exist between the molecules. For example, with water, the main force of attraction that water molecules sort of have between each other are hydrogen bonds. Now, for methane, which is a nonpolar covalent compound, there are some forces of attraction that do exist. We're not going to get into the details of all that. But what they are is that they are what are known as dispersion forces, which are essentially very temporary forces of attraction that result from momentary shifts of electron density. The main idea here is that hydrogen bonding and dispersion forces are not a match. Water exhibits hydrogen bonding as its main force of attraction between molecules. Methane exhibits dispersion forces as its main force of attraction. We don't have a match. Water and methanol, the main force of attraction between their molecules is hydrogen bonding. That really is a match. Here, you don't have a match. But on the other hand, methane can dissolve in a nonpolar, and I shouldn't say solvents, I should say solvent, okay? So methanol can dissolve in a nonpolar solvent. And this would be based on the idea of like dissolves like. Because in the nonpolar solvent, the main forces of attraction between the molecules would probably be dispersion forces, and now you have a match. So that the methane would be able to dissolve into water and such like that.